All right, let's start. Good afternoon. First of all, a reminder to find partners for your projects. We are going to post the first project this Friday, so try to find a partner as soon as possible. Again, if need be, we can have singletons, but really, I really prefer for you guys to work together. Okay. Again, let me know if you need help to find a partner. Piazza is a good place to shop around for somebody to work with. Okay. Any questions so far, or no? Okay. So the plan for today is we're going to finish talking about color. In particular, we're going to talk about representations of colors models, and then we're going to move into really study processing images. Okay. And so, as I mentioned the first day of class, computer vision needs to use image processing as the first stages of, because our input are images, right? So we need to do things with those images. Sometimes we need to clean the noise, we need to extract features, so we can actually go and then do some reasoning about what's going on. So for the next few lectures, we're going to be doing this kind of what's called low-level vision, okay? And it's low-level because we're going to be pushing pixels. We're going to just changing stuff instead of thinking in terms of objects, person, bicycle, right? We're just going to look at individual pixels, all right? Okay, so this is not working, so let me see. All right, so color models give us a way of representing color in the computer and to share among different applications and different hardware. And the basic idea you can think of is that we're going to represent colors in a coordinate system. And depending on the task that we need to work with or the hardware that we need to work with, one coordinate system might be more suitable than others. Okay? And can always go back and forth between these coordinate systems. All right? So we're going to discuss a few today. And they can be roughly split into two major groups. In one group, you have color models that are more suitable or helpful when you're thinking in terms of hardware. For example, a monitor or a printer. And there are some color models that are actually more suitable when you're thinking in terms of a computer vision application or software. Okay? And so on the hardware oriented, we have RGB, CMY, and YIQ. And then in the image processing oriented, we're going to talk about HIS and LAB. Okay? The main difference is for the image processing oriented is that they decouple the color information from the intensity information. Okay? And that's what I was mentioning last time, that, for example, it might be useful to detect faces in an image because everybody has more or less the same hue. Okay? So the RGB color model is the simplest model. It's the Cartesian model, right? And so you have three axes, one per primary color. So you have one axis for the red, one axis for the green, and one axis for the blue. Okay? And so a color is going to be given by an amount of red plus an amount of green plus an amount of blue. That would represent any color. Okay? Now, we saw last class that we could normalize the colors in a way. And for example, before we did it, that the sum of the three colors was equal to 1. We can also normalize such that the maximum amount of a color is equal to 1 and the minimum is 0. So we're going to basically work with this unit cube. The corner here has all zeros. So no red, no green, no blue. And of course, that means it's black. Right? I don't have any color in it. The corner over here has equal amounts of red, green, and blue, equal to the maximum, is the 1, 1, 1 point, and that's equal to white. Okay? This color over here has 100% of red and 100% of green and 0% of blue, and that corresponds to yellow and so forth. Okay? So this is the RGB color map. Let me see if I can fix my mouse. It's becoming example, in these three images, this one corresponds to the red band, this for the green band, and this for the blue band. Okay? And so this guy has all pixels the same value, say 127, which is roughly over here is bluish. Why is bluish over that corner?
Because the blue is white and all the other colors are
Right. Here I have a lot of blue, right? Here I have nothing on the green, and the red is kind of a medium. So it makes it a little purplish because I'm adding red to the blue, but it's still on the bluish side. Okay. Over here, this corner has no blue, and it has no green, but it has some red, so you see that corner reddish. Okay, and so forth. And so this is the cube again from the, and these are the faces that you don't get to see of the cube. Okay, and they can be done the same way. All right. Now those were a lot of colors. Sometimes people work with a lot less colors and still have very pleasant results and useful results. And the main idea is that these colors are considered, meaning that you from one device to another. Okay? And these 6 colors, they use 6 possible values to represent each of the bands. Okay? Now, instead of having a million different colors, now we only have 216 colors, 6 power 3. Okay, and we can represent those colors again on the cube, and that's how it looks like. So you see less number of colors, right? It's much more discrete. Before it was a continuum. Now I have only these few colors, and also now is the surface. I don't have any volume anymore. Okay. All right, so that's the RGB colors. And RGB color maps are good, for example, for cameras. So if I take the output of this camera, typically what I will get is 3 channels, one for red, one for green, one for blue. It's also good for monitors, again, by combining RGB together. Last time we discussed that for paper printing, for example, we wanted to having an additive model, we want to have a subtraction model, and so we use this cyan, magenta, yellow, black color model. And it's very easy to go back and forth between the two, right? These are the primary colors, these are the secondary colors, and it's basically just take the primary from white. White is 1, 1, 1, yes?
Is CMY always scaled between 0 and 1, or is it scaled up to the number of bits?
So you can play back and forth. So it's a normalization. So most of the time here we're going to be talking about 0 and 1, but then on your images you might represent it between 0 to 55. So again, you keep going one or the other depending on what you're doing.
Okay.
Okay. So if you want to work with integers, you work with 0 to 255. If you want to work with real numbers, then you have from between 0 and 1. All right? Yes?
To start the context question, like you are getting an image from the camera, which is RGB.
Yes.
So how are you getting, how does the camera capture RGB image?
So it has sensors that are sensitive to different wavelength. So you have basically like 3 CCD arrays together. And it's one that's sensitive to the red wavelength, one is sensitive to the green, and one is sensitive to the blue.
Okay.
Okay? So the number of photons that get captured in the array depends on the wavelength. Okay, so again, CMY is very easy to go back and forth with RGB. It's just a subtraction. Okay. The other color map I wanted to talk about is something that has to do with TV transmission. And over here, please, I need to make the difference between luminance and intensity. Okay, so this is a standard image that sometimes is used to calibrate color across devices. And what you see is I have strips of different colors, right? And in this end I have blue, in the other end I have red, and here in the middle I have green. Okay. Now, again, I could represent this in RGB, and so we have one band for the red, one band for the green, one band for the blue. Okay. Now, if I add them up, all the 3 bands together, and divide by 3, I get the average band. Okay. That average band is what we say is the intensity. It says basically how much energy, how much intensity I have the red plus the green plus the blue. Okay, and the image that I will get if I did that is this one. Okay, now qualitatively, if you look at this guy and this guy over here, of course they're very different because one is color and the other one is just grayscale. Okay, but it's also more that had been lost. If you look at the top image, I think you will agree with me that this green area seems to be brighter than the blue area and the red area. Yes? But here in intensity, that is gone. Because this image was done in a way actually that they all have the same intensity. Okay? So I lose some kind of perception of what was going on there. Okay? So now imagine that I'm transmitting this in color TV to your homes, and you're watching it on TV before you stream things in computers many years ago, right? And I'm streaming this, and you have a color monitor, and you will see this. But your friend still has a very old ancient black and white TV, right? And if I send the signal, this signal, to the black and white, if I don't do it properly, what he will see is this. And so not only he's being deprived of color, but he's also being deprived of some sense of brightness that's happening here. Okay? Now the bottom image over here is called the luminescent image. Okay? And you can see this also grayscale, right? But it has this thing that here looks like. Okay? Now any ideas of why we see this so flat, and over here we see this brightness might have been causing us to see these images this way.
Eyes are more sensitive.
Right, right. So we discussed that for us, blue always is darker than green, okay, because how our sensor is made. Okay, so this over here is trying to mimic better what the eye is capturing if we took away the color. Okay, and so this was devised when color TV started many years ago to try to give comparable signals to the people that are doing having only a black and white monitor. Okay, so the YIQ model separates the hue, okay, from the luminance. And so Y is the luminance, so that would be what you would transmit to a black and white old TV, which will, result in just one channel. It's grayscale, but it captures the way we perceive colors in a better way, okay, because it's giving more weight to the green, okay, and the least weight to the blue, right? So if you have something that has color, you reinforce the green and downplay the blue. And then the other portion here, IQ, had to do with actually the color, okay? So it has these funny numbers. Again, these are based on how the human eye works, okay? But again, it's a linear transformation, right? So if you give me RGB values coming out of a color camera, and you apply this matrix, and you get these white IQ values, okay? And if you just look at Y, what you're going to look is the grayscale image that represents the color image in a way that looks similar to what we would perceive if it was color. And then I and Q has the color that can be added later on to produce a color image. Okay. Now, again, let's talk about color models that are more suitable for computer vision. Okay. And again, we are going to be putting emphasis on hue and also on saturation. Okay. So the HSI model is a model that has again, 3 components, and separating the intensity. Again, the intensity is the average of the 3 bands. So now I'm not paying attention on how I perceive that intensity. I don't care about that. But I'm going to extract out the color in a way that I can reason about what's the hue and what is the saturation. Okay. So again, because hue and saturation have that powerful distinguishing properties, it's useful for computer vision. And what we're going to do for that is we're going to look again at the RGB cube, and I'm going to see where is hue and where is saturation represented in that cube. Okay? All right, so I want you to look at this cube. Again, it's a unit size cube. It has one corner is black, that remember was at the origin of the RGB color map. The opposite corner in the diagonal is white. And then I have the primary colors, red, green, and blue. And I have the secondary colors, cyan, magenta, and yellow. Okay? Now, if you look at the diagonal between white and black, and I move along that diagonal, okay, and I look at the points in that diagonal, what color are they? Gray, right? It has equal amounts of red, green, and blue, the primaries, right? So, but what is changing is the intensity. So if it was a full intensity, it was white. If it's at 0 intensity, it's black. And anything in between will be gray. Okay? So that diagonal represents the grayscale. Okay? Now, if I take one side of the cube, okay, say for example, the side between white and cyan, okay, and I consider the plane defined by the diagonal, that is, has a white and the black line, and the point cyan. So I have this triangle and I expand that triangle into a plane. Okay? All the points on that plane, what hue do they have? What is the hue? It's actually written on the slide, so it's kind of a silly question to ask. It's going to be cyan, but let's say why? Why any point on that triangle has hue cyan?
Because all you're changing is the intensity, it's independent of the hue?
Right, so you can say also that any point here is a linear combination of points enclosing it. Okay, so it's a linear combination of cyan, white, and black. Okay, so basically I'm just adding white to it. Okay, so what I'm going to be doing is changing the, what's the other property of color? Hue was one? Saturation, right? I'm going to be changing saturation. Okay. All right, so with that in mind, now I want you to play a little trick with your eyes and look at that cube here, which has been put in a way that that diagonal between white and black has collapsed into a point, right? I'm making the perspective. You're looking straight direct along that diagonal, and so it looks like a flattened, it's a 3D cube, but because of the viewpoint I have chosen, you see that as an hexagon. Yes? Okay. So this is what we're going to be representing now colors, because what we're going to do is imagine that diagonal and imagine a plane perpendicular to that diagonal. And that plane, when it intersects the cube, it looks like that hexagon. Okay? And what we see is that the primary colors, red, green, and blue, are apart 120 degrees. And the secondary colors, yellow, magenta, and cyan, are 60 degrees apart from from the primaries. Okay? Which also means that they are 120 between themselves, between the secondary colors. Okay? So what we're going to be doing is representing hue by an angle. As we move around this hexagon, we're changing hue. Yes? Now, how do I represent saturation? What can I do to represent saturation?
How far it is from the center?
How far is from the center, right? So instead of playing with this hexagon like this, which is, it's the 3D cube being flattened, I can directly go with an hexagon and represent hue by the angle. So if I have that color over here, this angle measures hue, and the length of this vector measures saturation. Okay? The farther I am to the boundary, the more pure the color is, the less white it has. As I'm getting closer to the center, I'm becoming dimmer and dimmer. I have more grays in it. Okay? Now, once you go to this representation, people have also said, well, why not represent that with a circle? Forget the hexagon. Right? I can always morph the hexagon into a circle, and really what I'm interested is in this angle and this distance. Okay? So you might see this represented as a circle, and even as a triangle. Again, you can morph that circle into a triangle. And again, what matters is angle. Measure here, and we have used, and that's the common practice, use red as my reference. So hue is going to be measured as an angle starting from red. Okay? Questions? No? All right. So what this does is taking those circles or triangles and actually make clear that we have different level of intensities, right? So when I show you that hexagon, I had collapsed my diagonal into a single point, but the diagonal is long. And so depending at which level I am cutting the diagonal, I have different amounts of intensity. And so that's represented now by having this smaller and bigger triangles, so it becomes like two inverted pyramids, one on top of each other. Or if I'm using circle, it becomes cones. I have two inverted cones. Okay, but it's the same idea. Okay, now I can put this back into the cube by having the relationship between RGB and HSI. Okay. Now you notice now that these equations, they look a little uglier than the equations I have, for example, to go from RGB to the luminescence YIQ model, right? There it was a linear transformation. It was a multiplication of a matrix. Here you see cosine inverse things, okay? And you see some minimum stuff. And so this happens because we have this angle going on here, right? So now my transformation is not linear anymore. Okay? It's sinusoidal. But it's an equation. It can be easily programmed, and MATLAB has already programmed for you. Okay? Now, again, so I can go back and forth. I can invert. I can go from RGB to HSI, or from HSI I can go to RGB. And if you do that, you start with a cube here that has RGB colors, for example, and you can compute for every point on that cube what is the hue, what is the saturation, and what's intensity. Right? And now I can display these cubes where now the value represented at each point is one of these components of the color, of the new color map. Okay? So here I have the hue Q, the saturation Q, and the intensity Q. Again, when I combine these three together in the proper way, I do get back these colors. Okay? Now I pointed to something here. If you look at the hue, looks kind of funny. Has a very sharp discontinuity at that corner. Can you figure out why that is happening? Yes?
On the equation, it's piecewise. That's where it jumps from the other.
It's not piecewise.
It's when the blue is greater than blue.
What happens is that hue, okay, is measured by angle, right? And so I start at 0, and I keep increasing my hue, right? And I end up at 360. And then I will have to start again at 0. So there is a jump between 360 and 0. It's an artifact of using angle as my representation for hue. Okay. Why is this corner very dark?
Because it's fully saturated, there's no color, it's just pure white.
It's pure white, right? So it's 0 saturation, and 0 means black, okay? And this is just intensity, all right? Okay, the last color map that we're going to use is one of, again, the most popular used in computer vision, is the LAB color map. And the characteristics of this color map, first of all, is that it tries to make it sure that the perceived intensity of the colors is the same across different people and different values. So we want to have a way of capturing the relative difference between colors. So if I think that these two colors are different by this much, okay, and these two colors are different by the same amount, I want to be able to be that consistent to the way that humans perceive that. And so based on that, the color, again, transformations have been derived, and with a lot of experiments with humans. And the idea is, again, that's device independent, that if I display using this color map in my monitor and your monitor, other monitors will be the same. Okay, so the transformations, again, are a little more complicated than linear. It has a square root, cubic root here, and there's some divisions over here. So they look uglier, but again, it's just a matter of plugging in numbers and getting back numbers. So don't worry too much about it. But what is important, again, is it helps to try to capture color instead of just intensity on the images. All right, so let's move to processing images. And we're going to be working with color images. And so the first question is, how do you do image processing in an image that has 3 bands? Okay. And I want first to make clear that actually you might hear about color processing, and people use that term in different ways. So one way is, we are more interested in this class, which is usually trying to find features or segmenting images that happen to have been captured in color. But also you might hear color processing in terms of what's called pseudo-color. And that's also very useful too. We're going to see that, in particular to displaying things in a way that are easily to understand. Okay, so we can make a color image up to of a grayscale image for the purpose of visualization. Okay, so which is different than capturing a color image and then doing some processing in it. So here we're going to start with a grayscale image and somehow make it color. And again, we want to be able to see things better that way. So this representation, what I have here, is a 3D color, a 3D reference frame, where the X and the Y axis represent the rows and columns of your image. And the vertical axis represents the grayscale value of this grayscale image. So I have one band only now. It has several rows, several columns. At each pixel level, it has at each pixel has some value. So I'm plotting those values as a function of the location. Make sense? What that plot means? Okay, so now what I'm going to do is I'm going to take planes that are parallel to the row column plane and cut this surface that's made out of the pixel values. And everything that is, say, above that plane, I color one color, and everything that's below, I color a different color. Or I can say some of these planes I'm going to color one color, and some other planes I'm going to color a different color. Okay? So if I do that, now I can do things like this. Okay, so I have this image. Okay, it's a monochrome image. It was done with just a grayscale sensor. Okay, and I want to visualize some structures that are happening here. And our eyes are not very good at distinguishing different gray level values. Okay, so we look at this, yes, we clearly see this hole over here, but over here we see some kind of texture, but it's really hard to figure out those boundaries because our sensors are not that good for that. Okay, but if we decide that the pixel values between 15 and 35, I'm going to paint them green, and pixel values that are between 35 and 75, I'm going to paint them red, and so forth. Now I started seeing this contour much easier. Okay, and this is what this is doing. Okay, so basically, depending on the grayscale value, a pixel was colored in a particular color. Okay, and again, the application is really just to be able to see. It's for a human consumption. It's not to make the algorithm any better. Okay. Here's another example. This is a map where colors represent the amount of rainfall monthly on the world. Okay, and again, in grayscale, it's kind of hard to see, but if you color it, then it's much easier to see where are places that you have a lot of rain and less of rain. So we see pictures like this all the time now, for example, where we're following the hurricanes, right? People color the images so we can understand what the values mean. Okay. So in general, you have some image that each pixel represents a function of location, x and y. So I have f of x, y. And then I can apply some kind of transformation to that, such that I get something for the red band, something for the green band, and something for the blue band. And then I send that to my monitor, and I look at them. Okay. So here's another application where that was done. And in this case, it was for detecting explosives in an X-ray image at, say, at airport security, right? So we have a garment bag with some clothing on it. Here's a hanger. So this is the image. This is the bag with no explosive in it. This is the same bag, and this thing over here is supposed to be an explosive. Okay, so the idea is I want to do image processing to detect that. I want to see where that is. If the operator is looking at the X-ray machine, you want to make it easier for him or her to see that explosive. Okay, so here what is done is taking these grayscale images, they have been colored. Okay, and for that means that you need to take the gray level value that was in the original capture image and decide how to paint it. Okay, so you have some value and you have to decide how much of red, how much of green, how much of blue I'm going to assign to that value. Okay, so here on the right hand side what you see is two different functions, set of functions that have been used to color these images. Okay, so the top here is how I map a gray value to red, and how I map a value to green, and how I map a value to blue. Okay, this color map has been used to colorize these two images. So these two images, I apply this color map, and I obtain the two images on the left. Okay, and what you see is that in this case, the explosive is very easy to see. Right? There's a lot of contrast between this red bar and the blue garment bag. Okay. Now, these two images were also obtained in the same way, but instead of using these functions were used. And now what you see is that over here, the explosive almost has disappeared. Okay, so it's very important how you pick those functions. Okay, now this looks sort of similar, but why do they produce such a different result? Well, these functions are basically periodic sinusoidal functions, right? And depending on where the gray values lie, you will be catching different things. So on this one, these bands, these two vertical lines are signaling the region that corresponds to the gray level values here of the explosive. Okay? And so what you see is that the gray values here of the explosive have, for the red, for the green, and for the blue, very similar values to what it will be assigned to the values that happens to be on the background. And that's why you see this part is red and this part is red. Okay. But these ones that had been shifted a little bit off, and now what happens is that you catch the sinusoids in different places when you see the explosive and the background, but you basically catches at the same time, at the same places, for the explosive and the garment bag, so now everything becomes blue. Okay, so it takes some experimentation, experience, and try to decide what is the right functions to actually be able to visualize or highlight what you want to see. Okay? All right, you can have many transformations, and you can have do that those transformations and then go to red, green, and blue. You can do all sorts of things to that sort. Here's another example where I have 3 satellite images from the DC area. This is the Potomac River. Okay, and so this is the visible red, this is the visible green, and this is visible blue. And when you combine the 3 together, you get this image over here, which is not particularly informative. What you see is some greenery, okay, and you see the river here. Now, if you add to that, if you replace the red, for example, with a near-infrared image, okay, what the infrared image is doing? What does it capture? Heat, right? And I replace one of my color bands by that. Okay? Now I'm going to have information about the heat of the scene. And what you see is this over here. And now we see, first of all, this has very bright areas, so everything now becomes very red, right? Because I put that image in the red band. So I have high values for red, number one. But the other thing is that now this thing is picking up the difference between vegetation and buildings. Buildings are cold, but vegetation and the river are warm. Okay, so you see the bluish stuff is where the buildings are, and the red is where actually the vegetation happens to be. So you can make all sorts of combinations or transformations of these images again to try to help visualize things that you are interested in seeing. Okay. Okay, so that's pseudo color. Okay. Now again, in this class, we're more interested on actually doing image processing to do analysis of images, not so much on displaying things pretty or in an understandable way. Okay, so we have to figure out, we have these 3 bands, how are we going to process them? Okay, and I'm saying all of this because in 5 or 10 minutes, I'm going to switch back to grayscale. Okay, and we're not going to talk on color for a long time, but we need to know how to do color. Okay, so there are 2 main ways of doing image processing on color images. Okay, one way is you process each band independent of each other. So basically saying, instead of having 1 image, I've had 3 images. Okay, and you do some processing in each of those bands, and then you combine them back together. Okay, and the other way is instead looking at each pixel as really a vector that has 3 components. how much red, how much green, how much blue, or how much hue, how much saturation, how much intensity. Depends on which color map I'm working on, okay? But each pixel now becomes a vector of 3, and now I'm processing the 3 images, the 3 bands together, okay? So those are basically the 2 ways you can do it, okay? You do it by slice, or you do it by pixel, okay? All right, so this is a preview of what's coming in a couple more slides, how we do image processing. A lot of the image processing that we do involves working what we call a mask, okay? So a mask is just a little image. You can think of that, I have a smaller image, usually is of odd sizes, 3 by 3, 5 by 5, 11 by 11, okay? And we're going to basically pass that mask, scan that mask around the image and do some computations. Okay, that's what we're going to be talking when we talk about filter. Okay, so now if I'm working with a grayscale image or just one band of my color image, right, then my mask is just one band also. Okay, so it has some spatial support, but no depth to it. Or if I'm working directly on the RGB using pixels, then my mask will become a volume. Okay, so it's not just one band, but it will have actually the number of bands that my image have. Okay, and again, in this class, we're going to talk about 3 bands, but I could have bands with multiple wavelengths. I could go all the way to infrared, different band, okay, and do processing on those. All right. Okay, so here is again a visualization of what these color maps mean, and working on the pixels by actually in tailor mean. Okay, so here I have this nice picture that is in full color. It has some bowl with strawberries and maybe a cup of coffee or something next to it. Okay, so there's a lot of white in it because maybe it's a tablecloth that's white, right? And the bowl that's having the fruit is white, and the cup of the coffee is white. And then I have very nice, yummy strawberries there, and they have very healthy green leaves to it. Okay, so this is, how the image would be displayed on the monitor. How, if I take a picture with my cell phone, that's how it would look like. And over here, what I have is the same image, but represented in these color maps. Okay, so the first row after the color image, this one here, what it has is the color map that would be used to print a picture of that photo. Okay, and so this band over here has cyan, this one has magenta, this one has yellow, and this has the black. Okay, so for example, all the places that are very white, it has very little or no black, right? And so that means that the image that has black has a lot of zeros. It only has high values where the image actually has black in it. So it's sort of almost like the negative of the image. Okay? Now, the magenta has a lot of high values around here because the strawberries, the red is close to the magenta, has a lot of magenta in it. Okay. The next row has the red, green, and blue. And again, you see that they look like grayscale images, sort of the original image, but none of them is really a grayscale representation of it. It's just capturing some of the colors, right? The primary colors, how much of each of those are there. And the last row is the one that has hue, saturation, and intensity. And here you see that this one, yes, it would be what we would think maybe of a grayscale image of the original image, right? It really has all the different things, except it's not having luminescence. So things do not capture the human perception of colors being brighter than others. Okay, it's just the average of the 3 intensities. Okay, so sometimes given a color image, what we're going to do is compute first the intensity image. So go to grayscale. For example, if you MATLAB, you do RGB to gray. Okay, it will give you that, and then you do image processing on it. We do, for example, edge detection on it, okay, as we're going to see next class. And then we go back and put that together with the other bands. All right? Okay. Questions about color before we move on? Okay, we are ready now to do image processing. All right. So you have seen my nice cow before. Again, the problem that we have when we do computer vision is that the computer only sees numbers. Okay, and again, for now on, I'm going to just work with grayscale images. Whenever we need to do color, we will get back to how we deal with that. But for now, just one band. So I have the intensity image, okay, and I have a bunch of numbers, and I want to do things with those numbers, okay. So for us, most of the time, these numbers are going to be represented with 8 bits. And so I will have, my pixel values will be between 0 and 255. Sometimes I will go back to the range between 0 and 1, and so I will have floating point numbers. Okay? Now, again, in a range 0 to 255 or 0 to 1, the lower the value, the darker the color is, the higher the value, the brighter the color is. So 255 is white, 0 is black. Okay? And we're going to be working with pixels and neighborhoods of pixels. Okay, so it's very important to have the concept of neighborhood. And we're going to distinguish 2 types of neighbors for a given pixel. So again, pixels are in a grid, so it's a very structured, right? My image is a matrix. And so given a pixel, I have 4 neighbors. The neighbors are the guy on the top, on the bottom, and to the left and the right, or north, south, east, and west. Okay, and these are the 4 neighbors. And so they have a full edge of pixel boundary between them. Okay, we're also going to consider 8 neighbors. Okay, which means to these 4 we add also the other 4 corners of the neighborhood of a 3 by 3. Okay, and so now instead of having just north, south, east, and west, I have north, northeast, east, southeast, etc. Okay, so these neighborhoods can be used, and this neighborhood can be used to define paths between pixels. And the reason paths between pixels are important is, for example, when I'm trying to model the contour, the boundary of an object. Okay? So we're going to distinguish between paths that are 4 connected and 8 connected. Okay? So here is my image, a grid. Okay? And I want to go from this pixel to this pixel, following some path. Okay? Now, if when I traverse from here to here, I always cross vertical or horizontal lines, then I have a 4 connected path. Okay? Because I'm always moving from my current location to one of my 4 neighbors. Okay? But I can also have an 8 connected path if I sometimes, not always, not necessarily always, but sometimes I cross across the corners. Okay, so instead of going across a vertical or horizontal, I go through one of the vertices. Okay, so that means given a location, now my next location is one of my 8 neighbors, and we call that an 8 connected path. Okay, all right. Now we're going to be doing computations with pixels and so forth. We're going to do a lot of pushing pixels. And depending on what level we work with the image, we will say that we work at a very low level or a high level. Okay, so low level is all the way down to the pixel, and high level is all the way up to the concept of a person or a building or a horse. Okay, so we have the object or the scene. Okay, so we're going to distinguish those levels, and so we have a graduation between them, depending on how much information we use to make this processing or reasoning. Okay, so the lowest level, which is where we're going to start today, is what's called the point level. Okay, and what that means is that my operations depend only on the pixel that I'm looking at. Okay, so that's the lowest I can go. Okay, so I have an image, and I want to create another image. Okay, and to decide what I will put in the new image, at every pixel of my given image, I'm going to do an operation. And the result of that operation, I'm going to put it in the same location on the other image. But that function that I'm using to do that depends only on the pixel I'm looking at. It doesn't depend at all on the rest of the image. Okay? Can you think of an operation that might be useful that would work at that level? actually finding an edge needs more than 1 pixel. I'm sorry?
Reduce the brightness of the image.
Reduce the brightness of the image, for example. I can scale every pixel value by an amount, okay? Or I can threshold my image. I'm going to find which pixels are greater than 130, okay? So I need just to compare my pixel value against that threshold value, okay? So I don't depend on my neighbors, okay? Then I move the next level, the local level. And edge detection is a local level, okay? By local, what I mean is that now the new pixel value depends not only on the location I am right now, but also of my neighbors, okay? The next one is the global level, and that means that to say what is the output at the pixel, I need to look the entire image. Do you have any operation that might require that? What could I want to do with an image that requires the whole image? Yes, recognition will require at least portions of the image, not necessarily the whole image. I can use context in the whole image, but tracking again, I might be. Let's not talk about video, but tracking it, I could still do it in a sub-region of the image. Sorry, transform. What kind of transform? Superpixel. Okay. Superpixel is again kind of local. You could do a Fourier transform, for example. Say I want to see the frequency components of my image. Okay? Then I need the whole image to actually find out what is the Fourier transform at a particular point. Okay? Also, if I want to do a histogram of the image, that's also, I need to look at every pixel to figure out how many pixels I have equal to 120. Okay, so that's also a global level. Okay, and then I have the object level, which is more like tracking or recognition. Okay, where I actually need to have some kind of grouping of pixels, which typically will not be along pixel boundaries, right? I would like to have the contours of the object. Sometimes we settle down, instead of having the contour, because sometimes that's complicated, we get a bounding box around the object. Okay. All right, so let's talk about filtering. Okay, and the filtering that we're going to talk about today is spatial filtering. What that means is I'm going to be processing just images, not video. However, for the project, you're going to generalize this to doing filtering along the time direction. Okay, and what's nice is that actually the concepts I'm teaching now can be directly applied. It's just you need to change the viewpoint of how you're doing things, but it's basically the same type of operations. Okay. All right. So, as I hinted earlier, a lot of the stuff that we're going to be doing for filtering will involve these smaller images that we call the kernel or the mask, okay, or the filter, and that's what we're going to be applying to our images. Okay. And we're going to discuss today, well, maybe today we're going to talk about linear, and maybe nonlinear we'll talk about on Friday. But we're going to see that filters can be either linear or nonlinear, and some they have some advantages and disadvantages, and sometimes we want to apply one versus the other. Okay. So a spatial filter will include some of the examples that we're going to see is we're going to see sharpening. We're going to see noise cleaning. We're going to see, which is basically a smoothing. Okay, we're going to see edge detection. Okay, all of these can be done using spatial filtering. Okay, so here's a general process. Okay, actually, let me do it on the board. For linear filters, we're going to be given an input image I. Okay, that has some number of rows, some number of columns, right? And I have pixel values, right? So this is say column row I, and this is column J. Okay, and I want to pass that through some kind of filter. Okay, which I'm going to implement with some coding, and the output should be another image that in principle we would like this image to be the same size. So if this is an m by n image, meaning that has m rows and columns, I would typically would like my output to have the same size. Okay, and so the task is now what number I'm going to put here at row I and column J. Okay, and so as I mentioned earlier, depending on the type of things we do, well, I can decide what to put here just by looking at this guy, or I might look at a neighborhood around it. And now what we're going to be looking at is operations that work with a neighborhood. Okay, and so that tiny image mask or kernel that we're talking about, what it's doing is telling you the scope of the neighborhood that I'm going to be looking at. Okay, so over here I draw a 3 by 3 neighborhood. That means that my mask is 3 by 3. My kernel is 3 by 3. Depending on what I want to capture or do with my image, I might decide to work with a bigger kernel. I might have a 5 by 5 or 7 by 7. Okay, the reason I pick odds is because I like to have a good center in my mask. Okay, so it's easier to have an odd number, so the middle column and the middle row gives me the center of the kernel. Okay, but that doesn't mean that you cannot have a kernel that's 2 by 2. Okay, you could. It's just it's easier to implement sometimes to have a nice odd number. Okay, all right. So what we're going to be doing is taking this kernel and slide it over the image, because we want to have a new pixel value at every location on my output image. Okay, so to figure out what to put here, well, I'm going to be looking at these 9 guys, for example, but to look what I put here, right, I will come to the same location here and also look at the 3 by 3. Okay, now the most common operation that we're going to do this is correlation. Okay, how do I do correlation? Anybody? I want to do the correlation between the mask and what's underneath the mask. You were going to say something. Suppose my mask, again, I'm drawing 3 by 3 because that's the easiest. It could be 5 by 5, 7 by 7. But let's call this M1, M2, M3, all the way to M9, right? What I'm going to do is I'm going to put the mask on top of the image and multiply the pixel values underneath the mask with the value at that in the mask at that location. Okay, so over here, this guy gets multiplied by M1, this guy gets multiplied by M2, M3, M4, M5, and 6, and 7, and 9, 8, 9. And then I sum them up. Okay, so what I'm doing is a weighted average of the pixel values in that neighborhood. Okay, what I'm doing is sum from I equals, say, 1 to 9, if I'm doing the neighborhood, okay, of 3 by 3, of the pixel values in that neighborhood times the values of the mask. Okay, so if you imagine if all these mask values were all equal to 1 over 3, or 1 over 9, I'm sorry, right? What I will be doing is summing up everybody and then divided by 9, which will give me the average. That's one example of the kind of filter that we're going to be doing. Okay, but again, what we're doing is just correlation, and what we do is we slide this guy all over the place, and at each time I do this computation, that gives me the number to put here. Okay? Now, this type of operation is a linear operation. Okay? And it's shift invariant. What does it mean that it's linear and that it's shift invariant? Yes?
I think shifting variant is, it doesn't matter if you go from right to left or left to right. The middle pixel will always be the same with the operation given in the matrix.
That's true. It also means that if I shifted my image and I apply the filter to the shifted image, I will get the same result as before, but just shifted. Okay? So because I shifted the things, the result does not change. Because I'm not really using the actual location of the pixel, I'm using the values in that neighborhood. So I'm not using that this is row I and column J. I'm just using what are the 9 values I have here to combine and give it back.
And there is using linear combinations of
Right.
pixels, so
That's linear. And the consequence of that is that if I have 2 images, and I apply a filter to them, and sum them up, the result is the same as applying that filter to the sum of the images. So I could sum first and apply the filter, or I can apply the filter to each of them and then sum them up, and I get the same result. And also this applies if I scale by a scalar. So if I multiply all my image by a scalar A, and this image, every pixel by a scalar B, right? This also is like that, but this is also A f of 1, B 2, and this is A f by 1 plus B f of by 2. Okay? And depending what I'm doing, I might prefer to do it this and then add, or I might first add and then do it. Yes?
Why don't you refer to this as convolution?
Aha. So that's a very good question. It's one of my next slides, but let's do it on the board. What's the difference between correlation and correlation? Actually, we do call this convolution, but it's incorrect. Why is incorrect? We don't flip, right? The convolution is the same operation, but you will flip one of the functions first. Okay? Here, we're doing the same thing that you probably have done in filtering in 1D signals, but we're extending this to 2D. Okay? And so this is the same operation, but now in 2D. And so we had to flip my kernel or my image. I could do either one. Doesn't matter which one. Okay? Now, the reason that, well, I don't know if that's the reason, but in the jargon of computer vision, this operation often is called convolution. I will convolve with my kernel, okay? And you are right to call it a convolution in some cases. In which cases is this a convolution? My kernel is symmetric. If my kernel is symmetric, if I flip it, I get back the same thing, and so I was right anyway, okay? Now, if my kernel was not symmetric, well, it's a stretch calling it a convolution, but people have done it. And partially, part of it is that computer vision sits right in the middle between electrical engineering and computer science. And so people that have a signal processing background are very picky about calling this convolution, because this is not a convolution. But people that come from the computer science background, sometimes they don't really get that difference. So that's why it got mixed many, many years ago, and now you read it as being a convolution. Okay? All right. Now, I said that typically I want the input image and the output image to be the same size. Okay? Does that bring any issues? Yes, what?
In the boundaries.
In the boundaries, right? Because what do I put there? What do I need to do?
The value around that pixel.
Right? So let's say again I'm doing a 3x3 neighborhood, right? Let me clean my input image. And let's say I'm doing a 3x3 filter, okay? So, and I want to decide what to put at that location, which means I need to put a 3x3 mask centered there, right? But the problem is that I don't have data there, right? So how do I apply that kernel in that location, okay? And there are different things that people do, okay? And depending on the application, one might be slightly better than the other, and many times it doesn't really matter, okay? First of all, how many pixels do I have this kind of trouble? All the edges. So these guys are sort of compromised that way, right? What if my kernel was 5 by 5?
That's the next.
The next inner circle, right? So the bigger the kernel is, the more pixels I have trouble with, okay? But again, typically my kernels are fairly small compared to the size of the image. So if I get the results in this frame of the image, even if it's a thick frame and they're not quite right, most of the time doesn't really matter. Usually what I'm interested in images anyway happens at the center. Okay. Now, if that's the case, why do I care about the input image and the output image to be the same size? I could just drop that, right? I could drop the frame. Only compute things where things are well defined. Why I might not want to do that? I'm sorry? I lose data. And then also if I have like a chain of transformations I need to do, every time my image gets a little shrinking and shrinking and shrinking, in the end I might actually have very significant smaller thing. And keeping track of the size of the images might be a pain too, depending on what you're coding, right? If it's MATLAB does it for you, but if you're doing in C or C++, then you have to carry the information and the size. So it's an option. I could drop the frame, and actually MATLAB allows you to do that. Okay, but if I want to keep the frame, I have to decide how to process these guys. Okay, and there are different ways you can do it, as I said earlier. Okay, one way is, for example, well, I don't know what it's there, so let's just put zeros. Why not? Okay, so now what happens is that this guy is really being affected by these three neighbors, not the other guys. Okay, and that's one possibility. Any other suggestions? Sorry?
Set them to 1.
So to what? That's also, yeah. Another one.
Just use 4.
4?
Like the rest of it.
Yes, this is what I mean. When I use 0, basically I'm using this 4. I'm not using this.
Could you like mirror those to the other side? Or is that kind of same thing?
No, I could do that. So there are two things. One is, let me first do the other one, and then I go back to the one you said. One thing I can do is think about how this image came about. So somebody pointed a camera to a scene and click, right? And that camera had some field of view, a limited CCD array. And that's why I'm seeing that rectangle or that square, right? But the world didn't end there, right? There was more world in the scene. I just happened to focus on taking your picture, right? So I'm focused on you but there's the rest of the room here with lots of people. Okay? So this boundary is sort of artificial. It's something that happened because my camera had a limited field of view. So what if the picture was being taken of the blackboard, right? So this pixel is black. And this pixel is also black because the blackboard continues. Okay? So black is not the best example because it's 0 again, but the idea is that neighbors' pixels are likely to have similar values. Right? My t-shirt is all green. So it doesn't matter whether you look here or here or here, it's green. Okay? So they all have more or less the same value. Okay? So another possibility is here to copy its neighbors. Okay? So I duplicate the first row, and I put it here. I duplicate the first column. I put it here. And here I have to decide what to do, but yeah, you get the idea. So that's one option. Okay. The other option is what he was saying, I think is what he was saying, which is to think of this as sort of a ball. Okay. So what I'm going to do is in here, this pixel, instead of copying my neighbor, what I'm going to do is copy the other extreme. And in here, when I'm going to copy not my neighbor, but this stream over here. So I'm wrapping out my image. Anybody with signal processing background, why that might make sense? It's like a circle thing. So what I'm saying here,
Maybe we can say circular convolution.
yeah, but what does it mean?
Polar coordinates.
No. What it means is I'm assuming my signal, my input signal, my image, is periodic. And the frame I'm seeing is just one cycle of my period. Okay? So instead of having one image, what I'm saying is, I'm going to draw it here smaller. Is that this image is a two-dimensional periodic signal, so I can copy this image here, 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 and also here, and here, and here. Okay? So now, if my signal is periodic, right, then yes, the neighbor of this guy, this side, is the end of the row, which is this guy here. Okay? So, for example, if you have something like a texture, this might make a lot of sense. Okay, so that's another option. Okay. Now, going back to convolution versus correlation. Okay. In MATLAB, you could use conv for convolution, or there's also a core command, or you can use infilter that allows you to choose which one you want to do. Okay, and so basically you just said that you want to apply such filter, and it will do it for you. Okay. Okay, so now let's talk about some particular type of filters. Okay. So again, in this class we're going to stay most of the time, like 90% of the time, in what say the spatial domain, which if you think of temporal signals is the equivalent, let's say, of the temporal domain. However, now and then we're going to be talking about the frequency content of the signal. Okay, and if you took the image processing class, or you will take the image processing class sometime with me, we do a lot of frequency domain. Okay, so we take the image, we do an FFT to it, work in the frequency domain, and then we come back to the spatial domain. In this class, most of the time our processing will be only in the spatial domain. Okay, nevertheless, we will talk about the frequency components of the image. Okay, and we're going, for example, today to talk about smoothing my image in an effort to clean noise, okay, to reduce noise. And for that, we're going to use a filter, which is basically a low-pass filter. Okay, what that means is that it keeps safe the low-frequency components of my signal and stops the high-frequency components. Okay. And the result of doing that is that our image, might have less noise. We're going to see in a few slides why that might be the case. But also we're going to have images that look less sharp. There's going to be blurring in my images. Okay? And the reason is because the edges happen for high frequencies. Why? Because you have a rapid change in grayscale values at very small support. Okay? Edge detection, on the other hand, is trying to find places where those rapid changes happen. And so it's focusing on the high frequencies. Okay, so our edge detectors basically are high-pass filters. Okay, and of course you can have filters that are working in the middle. Okay, that are band-pass filters. Okay, so they remove some low frequencies and remove some high frequencies and let pass some frequencies in the middle. And those typically are used for image restoration, but not for enhancement. Okay. All right. Well, we did this. Here is an example of the correlation. Okay. So here's my kernel. Okay. 3 by 3. Here is the image. I'm going to apply that kernel on that. Again, what I need to do is slide this guy over it and do the sum of the products, okay? And over here, I chose the simplest way, which is let's expand the image with zeros, okay? So now that means that the pixel value over here is going to be the product of these 4 guys with these 4 guys on the sum. So 2 times 2 is 4, 2 times 1 is 2, 1 and minus 2, add them up, and you get a 5, and that's what goes there. Then you slide it to the next, and the next, and the next, and you compute things, and then you think, okay? All right, we discussed this, okay? So the wraparound, expanding, or cropping. We talk about the difference between correlation and convolution. So let me skip this. Sorry, guys. And let's now talk about image noise, okay? So it's a sad fact of life that doesn't matter how much money you pay for your camera, your images have noise in it. Okay, and noise is kind of tricky to define because depending on the context that you're talking about, noise could be just small fluctuations due to illumination. Okay. But it could be also a scratch on your lens, right? And that produces an artifact in your image. It could be clutter that is obscuring some of the stuff that you want to do. It could be fog that doesn't let you see very well what your objective is. So noise could be a lot of things. It's typically what I wish it was not there. That's the definition, right? So if it's there and I really impeding me doing what I want to do, I can call that noise. Okay. Now, in this class, though, we're going to be really looking at noise from a random point of view. Okay. So if it's a scratch on the lens and I know exactly where it happens in my image, I can avoid those pixels. I can ignore those pixels because I know that they come from the scratch. Okay, so I'm not going to be worrying about that kind of defects now. Okay, now what I'm more interested in is in how do I get rid of noise that comes, for example, because of the fluctuation of the light, because numerical accuracy in my computer, right? So if I have at some point I find a precision, I cannot represent an infinite number of bits. So I have rounding errors, for example. Okay, so all of that kind of noise is what I'm going to try to clean next. All right. So here's an example that tries to illustrate how noise affects my images, and it might eventually affect what I'm trying to process. So this is a very famous image in the image processing community. It actually comes with any MATLAB package. It's called the cameraman image. You might recognize the neighborhood. Yeah? Do you see where it is? Do you recognize this building in the back? That's MIT. Okay. So this guy is taking some videos or images. Now what we did is we took a little patch around his eye and we blow up the pixels, right? So this is just a copy of that, but now each of these rectangles, these squares, represents the value of the pixel. And you can see sort of the eye, right? You see the pupil, and then you see, or maybe the eyebrow, I don't know. And this is part of the hair, right? You see black over there. And then you see his skin, which is lighter, right? So now again, if I show you just this, it's very hard to figure out what you're looking at. But in this context, now I can do an interpretation of what I'm seeing. Now, we're also going to look at these pixel values, not just as flat image, but as a surface, okay? And so here what we see is we are plotting against the rows and columns, the location of the pixels, the gray value. Okay? All right. So again, this portion shows portion of the face, the hair, the eye. So you see different grayscales. Okay, good. And this looks fairly smooth. So you say, you know, what noise are you talking about? This looks nice. Now let's take another patch of the image. A patch, for example, here on the sky. Okay. And when we look at those eyes, with our eyes to that region of the image, either to the picture or directly to the scene, we basically see the same color, right? Remember what I was saying, that we are not very good at seeing difference in gray levels, okay? So you would have expected, if your camera was really good, I spent so much money on this camera, right? I would expect that region to be fairly flat, right? When I plot this in 3D, what I would like to see is a plane. But what we're seeing is this, okay? So you see that there's a lot of variations over there, okay? So where did the noise come from? Well, as I said earlier, it could come from fluctuations in the light, sensor noise. If your camera is getting warmer, that introduces extra noise. Quantization effects. Okay, final precision when you're doing operations with the image. So all of these are sources, okay? And again, we're going to think of them as random noise. And the good news is that it gives us tools to deal with noise. Okay, we can do signal processing. The bad news is that we need to talk about probability. Okay? All right, so here's another patch on the sky. Again, you would think that this would be flat, but instead, is this very peaky kind of thing. So I would really like this surface to be smoothed out to something more like this. Okay, it's not really constant. There is a gradient over there, maybe brighter on top and darker in the bottom. But I really would like a smooth thing, not this rough surface. Okay, so what we're going to be working on is how do I go from something like this to something like that, that hopefully respects the original signal, the signal that didn't have the noise, okay, and gets rid of the noise as much as we can. All right, so as I warned you, we're going to talk a little bit about probability. Luckily, I mean, it's very simple probability we're going to do in this class, mostly just expectation and conditional probability, but that's about it, okay? So let me first talk about like what we intuitively think about probability. which is basically a limit of a frequency ratio, right? So if I flip a fair coin many, many, many times, and I count how many times I have heads and how many times I have tails, I would expect 50%, 50% if it was fair, right? So that's what our intuition says about probability. So here I have the number of times an event happens, okay, over the number of times I try, and the limit of that ratio as the number of trials goes to infinity is what I okay. More formally, okay, to define probability, what we need to have is a set of all possible outcomes. Okay, we call that our universe, omega, big omega. Okay, and then we have events in that set, and we call that little omega. And then I can have subsets of events, and we're going to represent that with capital letters like A. Okay, and so now I have to have these following properties to have defined probability on the set omega. First of all, probabilities are always positive. Okay, so always greater or equal than 0. The probability of the universe is equal to 1. Right? Something has to happen. And if I have two subsets that are not intersecting, the intersection is empty, okay, then the probability of the union of these subsets is equal to the sum of the probabilities. And the probability of nothing happen is equal to 0. Okay, so these are the axioms for probability. And one of the concepts that's going to be important for us is independence. Okay? In particular, most of the time, we're going to assume that the noise value at a pixel is independent of the value of the ideal pixel at that location. Okay? So the noise doesn't know how bright or dark that pixel is. It's just being added to whatever it is in there. Okay, so independence happens all the time, or we like to assume independence if we can. It's helpful in the operations. And what it means in mathematical terms is that if I have a set of events A, B, and C, the probability of all of these events happening, if they are independent from each other, to the product of the probabilities of each of them. Okay. And again, what independence means is that knowing that one of these sets happen doesn't inform me at all of what are the chances of the other set happening. For example, the fact that today is Tuesday doesn't tell me anything about whether it's going to be raining today or not. Right? The day of the week should be independent of the rain, although sometimes it seems that it always rains when you have something that you want to do outdoors, but that's a different story. All right? So we can represent this with Venn diagrams. Here what I have is the whole universe represented with a rectangle, omega. I have a set of events in omega that I call A. I have another set of events that I call B. Okay? In this case, the way I draw A and B, they intersect. Okay? So I have the intersection between the two sets. That's A and B. Okay? That means that in this region, it's true that A happened and also that B happened. Okay? Now, if I tell you that B has happened, right? What can I say about the probability that A is also going to happen? How are they related? Does it help me knowing that B happened? Yes. Why? If B happened, right, and A is going to happen too, it has to be intersection, right? So what it means that now the possible A events that are compatible with the fact that B has happened, right, are only on the intersection. Okay? So now what I need to figure out, what is the ratio of the elements on that intersection and the elements in A, right? So it's like now my universe has shrunk. and the universe has rank to not the purple thing, but just the black thing, right? Because I know I am in B. I don't care anything outside B. Okay? So the probability of A given B is equal to the ratio between the probability of the two events happening together, the intersection, over the probability of B. Okay? The most useful equation in probability is the Bayes theorem. Okay? And it comes from this conditional probability that we define here. So again, the notation here, the bar means that probability of A, given that I know that B has happened. Okay? And I can multiply this term by P of B. And so I get that probability of B times probability of A given B is equal to the probability of A and B together. Right? But A and B together is the same thing as B and A together. There's no ordering on that. And so I could have done the equation as the probability of B given A. Right? And then the only thing it would be that in the difference is that in the denominator I would have A instead of B. Right? And so now I have that the probability of A and B is also probability of B given A times P of A. So this equation over here, and what else is allows me to swap the order of the condition versus the observation. Okay. Couple more things and then we can quit for today. Another thing that's useful is to be able to accumulate probabilities if we know partial probabilities. Okay, and so for that, what we need to have is a partition of the space. What I need to have is a set of subsets such that the union gives me the space I am interested on, and at the same time, these subsets are not intersecting; they're disjoint. Okay, so if I have my universe omega, and I split it into subregions, and each of these regions do not intersect with each other, and they cover the whole space, okay, which are these two statements over here. The intersection is empty, and the union is omega. If these two things is true, then I can write the probability of B by computing the probabilities of the intersection of B with each of the subregions. So I have P of B intersection SY, and then I sum up over all, and that will give me the probability of B. Okay, so that's another useful property. The other thing is we're going to model noise or probabilities using the probability distributions and density functions. And so for that, we're going to have random variables, which means that to an event in the universe, we're going to associate a number. Okay, so here I have an event omega. I associate to it some value, okay, that we call a random variable. I could also associate a vector, and then I would have a random vector, okay. But let's now, for now, talk about scalars. So x is a number that is associated with event and is random. And now what we're going to do is consider two things that are very useful, which is the distribution and the density of those random variables. Okay, so the distribution is a function that, given a value x, computes what's the probability, or tell us what's the probability of the random variable being less or equal than that x. Okay, and the density function is the derivative of this function. Okay, so this is the cumulative one, and this is the density function, and we abbreviate that by PDF, probability density function. Okay. Now, because of the properties that we have to define a probability space, it's always true that if I sum all my probabilities on the universe, has to be equal to 1. And if that universe happens to be continuous, instead of summation, I have integration. So the integral between minus infinity to infinity of P of x has to be equal to 1. And what that means is if I integrate the area underneath the curve of a PDF, it is equal to 1. Okay? Now, we're going to use many, many times two concepts about this, which is the expected value and the second order moments and the variance of a random variable. So the expected value is what is the value that I expect this random variable to have in average, okay? And this average is a weighted average. So what we need to do is for each possible x value, I'm going to weight that value for the probability of that value happening. And then I'm going to sum over all possible values. Again, the continuous domain, that's an integral for the range of x. And what I have x this time is probability, and that will give me the expected value. If instead of in this integral I put x squared, now we have what's called the second moment of the random variable. Okay? It's again a weighted average, but now I am averaging the square of the value instead of the actual value. Why is this useful? Well, this is useful because it's very related to variance. And the variance, what it does is measure how far is the value that I'm seeing from its expected value, right? So the expected value is what will happen in average. I then do an experiment, and of course, in general, that will not be the expected value. I want to see how far it is, right? And the measure of that is the variance. So what I want is the expected value of the difference between x and its expected value. And because I don't care whether it's less or greater, I do the square of that. Okay, so I have the expected value of the square of the difference, plug that in the integral for the expected value, expand this, and now what I see is I have is the expected value of the x squared, which is the second moment, minus the square of the first moment. Okay, and that's the variance. And we all know how to estimate that from a number of samples, right? So if I have n samples, I'm sorry, and the standard deviation is the square root of the variance. If I have n samples, I can estimate the mean by just averaging them. And I can also find the variance by using this approximation, right? So let's stop here. And with these concepts, on Friday, what we're going to do is how do we design a filter that actually removes noise? And how do we know that it's actually doing a job and how good the job is? Okay. And then we're going also to talk about nonlinear filters for noise cleaning. And then we're going to start talking about edge detection, which is also another type of linear filter. But now instead of doing averages, what we're going to be doing is differences. Okay. So see you on Friday. Again, try to find a partner as soon as possible. Yes?
How do we submit our homework?
So your homework, you need to scan it or write it in an electronic form and submit it to Blackboard. Okay? Thank you.